So matrix multiplication, yeah, you'll recall my amazing map from yesterday, and there it is, and it led to this matrice, which represented the number of connections between pairs of towns. So I set it up originally as a table, which was this one here, and you could see that A to B had one connection, and that was this road, and that meant that B to A also had one connection, which is the same road. So we got that symmetry across this diagram as well. My question is, how do we multiply matrices and why? And this comes back to something I talked about with you yesterday, which was when we developed multiplication in our arithmetic system, it had a purpose. It had that grouping purpose. It was there because, you know, we might say we have 3 groups of 7 pens, and we could then determine that was 21 pens. But that was just defined, so we could have defined that differently. Now we get a chance to start thinking about how would multiplying a matrix be useful. So I'm going to ask, what does r times r mean, i.e. r squared, and what about r cubed, and how would you represent that mathematically? I'm going to pause this a second. I think it's back on now. Okay. So our thoughts were good and thoughtful. We looked at this purple example, but it had no meaning because it doesn't have a context. I'm going to show you that specific multiplication now. Here is matrix multiplication. If you want to write it down, you can. This is my best effort at a diagram that's colourful and as clear as I can. But it's very procedural. I've got a note down here that says it's entirely procedural, but it is a little bit complex. So let me show you. If you have two matrices, A and B, then A times B is A times E and then B times G. So it's the first row times the second column gives you that first cell. And then the first row times the first row times the first column here, the first row times the second column in B gives us cell 1, 2. So this is cell 1, 2, first row, second column. That's where the 1, 2 come from. Second row, first column, give us cell 2, 1. And second row, second column, give us cell 2, 2. So I've got each of these cells labelled here, and hopefully you can see the pattern. Top row, left column gives us top left cell. Top row, right column gives us top right cell. This is just for a 2 by 2, but the pattern follows for all of them. Bottom row, left cell gives us bottom row, left column. Bottom row, right cell gives us bottom row, right column. So hopefully the colours make that as clear as I can make it. And the multiplication goes in order. C is the first value in that bottom row. It multiplies by the top value in the right column. So we get CF plus DH. Yeah.
Does it work the same for a 3 by 2?
Almost, and that's going to be my next question. It does work exactly the same for all square matrices, but some matrices can't be multiplied. Some can, some can't, and there's a very particular reason to do with the order. So start thinking about that now. But I'm going to give people time to copy this down. So I've underlined there and made the statement, this is very procedural. So it looks tough to start with, but it is really procedural, and there is some really distinct patterns to it. So I've got here 3 matrices, A, B and C. My question to you is, before I define when and where we can multiply matrices, my question to you is, which of those do you think we can multiply? And I'd like to do the calculations.
All of them.
The answer is not all of them.
2 of them. C and A.
C and A can be multiplied, but under certain conditions. A and B. Okay, so think about this. So you're saying A and B. So are you saying A times B, or are you saying B times A?
Hold on. A times B.
A times B. Shall we do A times B and have a look? I want to get to the point where you're telling me what is important to make something multiplicative. So let's start with A times B. There's a few options here, so we're going to do a fair bit of multiplication here. I'll start with A times B over here, and A times B is 2, 3, 3, 2, 2, 3 times 1, 2, 4 2, 2, 3. Before we start, I've got this little extension question down here. Is matrix multiplication commutative? Does anybody know what commutative means? Commutative. Does anybody know what commutative means? Okay, so that question is, does A times B equal B times A? That's what commutative means. Multiplication in the number system is, because 3 times 7 equals 7 times 3, and that works for all numbers. Does it work for matrices? Is that true? I'm going to give you a chance to vote. I'm going to record the vote on this video. I won't say who, I'll just say the numbers. Hands up if you think it is true.
Wait. Hold on, let me get this right so I don't stuff on my highlight. It wouldn't be asking if it...
Hands up if you think it's not true. So excitingly, the vote is 2 say true, 8 say not true, and 3 people are MIA for some unknown reason. So it's just a vote, bit of fun, and we'll have a look at it in a minute. You'll get the answer in a minute. If you think you know the answer at some point, you can tell me, but let me do this example first. A times B is equal to the top cell on the left-hand side will be the top row times by the left column. Except we'll get this. We'll get 2 times 1 plus 3 times 2. Everybody happy with that? So I've just done the obvious first value times the obvious first value, the obvious second value times the obvious second value. And then my next one will be the top row times the second column. So, and that will give me the top row, second column in my resultant matrices. So that will be 2 times 2 plus 3 times 2. And then my next one will be the top row times the third column. And that will give me my top row third value in my new matrices, which will be 2 times 4 plus 3 times 3. And now moving to the second row. So the second row is 3, 2 in the first matrices. 3, 2 times the first column will give me the second row, first column of my new matrices. 3 times 1 plus 2 times 2. And I'm going to storm on now. Second row, second column, 3 times 2 plus 2 times 2. Second row, third column, 3 times 4 plus 2 times 3. Now I've also got a third row though. Sorry? 2 times 1 plus 3 times 2. 2 times 2 plus 3 times 2. And 2 times 4 plus 3 times 3. They're not all this big. In fact, this is the biggest, and Chris chose it. So if you don't want to blame anybody, thanks, Chris.
No one likes you, Chris.
That wasn't actually what I was intending, but 8. So 2 times 1 plus 3 times 2 is 8, and then 10, and then 8 plus 6 is 14, and then 7. And 6 plus 4 is 10 again. Correct. Keep an eye on me, I'm feeling under pressure here. 18, what's that, 8, 10 again. And then 8 plus 9 is 17 again. So we get that result there. And there's our vector A times B. Does anyone have a guess? If I'm going to do B times A, does anyone want to change their original vote?
Yes. No, because of the column.
So don't do that, please. So do you want to say that it is true now?
Yeah.
Okay. Anybody else? I'm going to swap A and B around on here.
Oh my god.
It's going to be the same.
Okay, there's B times A. I'm going to tell you the answer now, whether it's going to be the same or not. And the answer is, it won't be the same. On that front though, and I'm going to tell you why, the main reason why, well, one of the reasons why, but this is the obvious reason why, the dimensions are going to change. Can anybody guess how big this next matrix will be?
Big.
Is it going to reflect?
No, it won't. The dimensions are going to be different. Anybody want to have a guess what the dimensions of the next matrix will be?
2 by 2.
It will be a 2 by 2 matrix rather than the 3 by 3 matrix. So what's the arithmetic here? My 2 by 2 matrix, I get the top row, I multiply the top row by the first column. So that's the top row there by the first column, and it gives me, and this time I get 3 things to multiply. 1 times 2 plus 2 times 3 plus 4 times 2. And then my next row, top row, second column, is 1 times 2, no that's wrong, sorry, 1 times 3 plus 2 times 2 plus 4 times 3, and then I get 2 times 2 plus 2 times 3 plus 3 times 2, and then I get 2 times 3 plus 2 times 2 plus 3 times 3, and then I'll get one of these wrong and you can correct me. Let's just pretend I'm doing it deliberately. 16, 3, 7, 12, 19, 10, 16, 10, 19. Now I've chosen very similar numbers, just coincidentally. I just wanted to keep my numbers low, and so the fact that 16, 16, 19, 19 is more coincidental than anything. Are they all right? Yes.
Tell your YouTube channel I'm a genius.
Change what's that?
Tell your YouTube channel I'm a genius.
Are you genius?
Don't do it.
No. That's it. That's matrix arithmetic. So the answer to the extension question, is matrix arithmetic or matrix multiplication commutative? No, it's not. And it never will be unless you've got really distinct square matrices. They have to be square matrices to start with, and they have to be quite similar. So you might get some that are different. If you were squaring, you'd get the same, obviously, but otherwise they'll be the same. Can I just make this note? Over here, you had a 3 by 2 times by a 2 by 3. You'll note here that the 2 and the 2 are the same. You can't see that anymore, can you? Let me just delete that. The 2 and the 2 are the same, and the 3 and the 3 identify that this is 3 by 3. So this 2 and 2, they have to match. So you've got the same number of values here as you have there to do your multiplication, otherwise it doesn't work. So sometimes it doesn't exist. There's no answer that exists, and 3 by 3 is your resultant matrix here. So your dimensions are really important here. And the most important thing is that your dimensions there have to match. But please note that you do get multiple choice in your exam, term 3 exam, and your external exam. And a really good multiple choice question would be to get this and say, if I do A times B, what will be the dimensions of my resultant matrix? I don't want you to go through this process. I want you to understand that the resultant matrix will be 3 by 3. Connor.
Does that mean you can do A times C but not C times A?
A times C will work because you will get, you'll get 2 by 2, but C times A will be 2 times 3 won't work. That's correct.
How would you work? Can you show how that would work?
What, A times C? A times C will equal A, what's A? 2, 3, 3, 2, 2, 3, times by C, which is 1, 1, 2, 2, a very boring matrix. And just note here that this is 2 by 2, so it will work, and the resultant matrix will be a 3 by 2. And we can get that from our remaining dimensions. So I get 2 times 1 plus 3 times 2. That's the top column by the first row. The top row by the first column, sorry. And then I get the top row by the second column, gives me 2 times 1 plus 3 times 2 again. And then I get 3 times 1 plus 2 times 1, 2 times 2. 3 times 1 plus 2 times 2. Then I get 2 times 1 plus 3 times 2, and 2 times 1 plus 3 times 2. And it gives me this. Overall, A times C is 8. I'm struggling with this arithmetic. 8. This should be the same on both sides. 3, that's 7, 7, 8, 8. There's my result matrix. But I can't go the other way because the dimensions will be out and I'll have an issue. I'll have a disconnect.
So could you do C times B?
So if you
So is there no solution for C times A?
C times A, no solution. Can't be multiplied. Okay?
Could you do C times B?
You could do C times B,
But no B A.
no B times C.
if there wasn't any more columns, you would just go for the last column again.
What?
Because look, the 3 times, the 3, 2 and the 2, 3.
Hold on a second.
You both multiply.
So I'd like to fill in the blanks. These are the rules. Rules for multiplication. For A times B to exist, and I probably should have written that there, to exist, A must have the same number of what as B has what.
Boom! And the resultant matrix is the vice versa.
Yep. Have I written that down somewhere? I don't think I have. If A is an n by m matrix, B is an n by p. Yeah, that's question part 4. A times B and B times A only exist if what? If they are...
The same. B is the identity matrix.
So if they are square or inverted dimension. So square means if A is an n by n times B is an n by n, that will work for both ways, A times B, B times A. But also if A is n by p and B is p by n, that will also work both ways because the p's will match up one way and then the n's will match up the other way. So, but they have to be 3 by 2 multiplied by 2 by 3, or 4 by 2 multiplied by 2 by 4. So you see how that's inverted? A squared can only exist if A is a something matrix.
Identity.
Nope. Square.
Oh, that's...
So, but it makes sense, doesn't it? Yeah? And if A is an n by m matrix and B is an n by p matrix, then A by B is an m by p matrix. That's that statement that Max was making with part 1. So that's the rules of matrix multiplication, and I'm going to leave it there. I've got some further examples for this topic to go through, but only a couple, and I'll do those a little bit later in the lesson. But for now, you can do these things. I should stop the video now. 17A, B and C. Let's just stop the video on a highlight. This is me ranting now. Still haven't stopped the video. And I'm going to stop the video there. See you later.